আজকে আমাদের নতুন একটা হচ্ছে টপিক, ঠিক আছে? স্যাম্পলিং কোয়ান্টাইজেশন থিওরি অ্যান্ড প্রিন্সিপাল লিনিয়ার সিস্টেম অ্যান্ড কনভলিউশন অ্যান্ড কন্টিনিউয়াস ডিসক্রিয়েট ফরিয়ার ট্রান্সফর্ম সব কিছু আমরা আলোচনা করব। ওকে, তো তোমরা দেখো, আমাদের ফার্স্ট হচ্ছে ইন্ট্রোডাকশন, হোয়াট ইজ দ্য স্যাম্পলিং অ্যান্ড কোয়ান্টাইজেশন। ওকে, তো স্যাম্পলিং কী এবং কোয়ান্টাইজেশন কী সেটার সম্বন্ধে প্রথমত তোমাদের জানতে হবে। ফার্স্ট হচ্ছে what is the sampling and quantization? The basic idea behind the sampling and quantization is the illustrated in the figure number 1. তো ফিগার নাম্বার 1-এ একটা হচ্ছে আমরা ইমেজ দেখতে পাচ্ছি। তো এটাকে আমরা যখন এটা কন্টিনিউয়াস ইমেজ আছে, যে ইমেজটা হচ্ছে এ এবং বি দ্বারা ডিজিটাল ফর্মে সেটাকে রিপ্রেজেন্ট করা হচ্ছে, এবং পরবর্তীতে স্যাম্পলিং এবং কোয়ান্টাইজেশনকে ডিজিটাইজেশন প্রসেস করা হচ্ছে। ওকে, তো অ্যান ইমেজ মে বি কন্টিনিউয়াস উইথ রেসপেক্ট টু দ্য এক্স অ্যান্ড ওয়াই কোঅর্ডিনেট, অলসো দ্য অ্যাম্পলিটিউড ভ্যালু। তো দেখো এখানে বলা হয়েছে ডিজিটাইজেশন কি এবং স্যাম্পলিং কি। স্যাম্পলিং বলা হয়ে থাকে তোমার ডিজিটাইজিং কোঅর্ডিনেট ভ্যালু কল্ড স্যাম্পলিং অ্যান্ড ডিজিটাইজেড অ্যাম্পলিটিউড ভ্যালু কল্ড কোয়ান্টাইজেশন। তো কোয়ান্টাইজেশন এবং স্যাম্পলিং দুটি জিনিস। প্রথমত ডিজিটাইজেশন কোঅর্ডিনেট ভ্যালু আমরা হচ্ছে সেটাকে বলবো স্যাম্পলিং, এবং ডিজিটাইজিং অ্যাম্পলিটিউড ভ্যালুকে বলবো কোয়ান্টাইজেশন। ওকে, দ্য ওয়ান ডাইমেনশনাল ফাংশন and a plot amplitude intensity level value continuous image along the segment A and B. তো কোনো একটা ইমেজে দেখো, কোনো একটা ইমেজ যেটা হচ্ছে তোমার কন্টিনিউয়াস ইমেজ আছে, এবং এই কন্টিনিউয়াস ইমেজকে তার অ্যাম্পলিটিউড বা ইন্টেন্সিটি ভ্যালুকে আমরা দেখতে পাচ্ছি এ এবং বি ইমেজ দ্বারা। ঠিক আছে, এ এবং বি যেটা ইমেজ ফিগ নাম্বার 1A সেখানে আমরা দেখতে পাচ্ছি। দেন দ্য রাইট সাইড ফিগ নাম্বার হচ্ছে দ্য 1C, this is show that the intensity scale divided into the 8 discrete intervals and ranging from the black and white. So then we have to see that the sampling the horizontally and A and B the fig number image is quantization, and we have to show that the black and white, and starting at the top of the image the carrying out this producer line by the line produce a two-dimensional digital image. Okay, এখানে আমরা দেখতে পাচ্ছি and last we have to seen that the two-dimensional digital image. So we have to seen that this slide at first we are know that the what is the sampling, what is the quantization. So we have to know that digitization amplitude value called sampling, coordinate value digitized amplitude value called quantization, and digitizing coordinate value called sampling. So we have to coordinate value the vertically coordinate value we have to see that this is the vertically, we have to this is the horizontally this is called sampling, and digitizing amplitude value called quantization. Okay, then we have to see that a amplitude intensity level value continuous image. Then this image we have to convert to the digital form, gray value, black and white. Okay, this is the introduction portion, sampling and quantization. We move forward the sampling quantization are the process that is use convert. How to convert the sampling quantization at the process that is use convert. Then we have to see that the analog convert by digital image, black low intensity and white very high intensity. So we have to see that there are three types of converting image. So analog image we are convert to the digital image, black portion we are converting the low intensity, and white portion we have seen that the very high intensity portion. Okay, the high intensity level is the shown that the upper portion, and we have to see that the low intensity portion this is the lower portion, and the shade of the gray is the between white and black. Okay, so shade of the gray value is the we have to see that it is the white and black portion. Okay, so we have to see that there is a intensity and gray and gray value, white and black portion. This is the one continuous image, then we have to convert. This is the digital form, this is the high, upper portion is the high intensity, and this is the lower portion is the low intensity. Okay, then we have to move forward. Here we are the sampling image, and which mean we dividing into the smaller equal parts. So we have here we sampling the image, which means we dividing into the smaller equal parts. Then quantization and sampling, the digitizing of the intensity of the color, as it can also have the identify value. Okay, then we have to, this is the identify value, this digital intensity color, as it is the can also have the infinitive value. Okay, digitization intensity of color, as it is can also have the infinitive value. And quantization, we have to seen that quantization, we have to seen that this is the black portion and the gray portion. Okay, and we have to seen that there is the coordinate value called sampling and the amplitude value called quantization. Okay, then due to storage and quantization hardware and the consideration, the number of the intensity level and the typically in the integer power of 2, L equal to K, and we assume to the discrete level at the equally pace, and they are the integers in the interval 0 L minus 1 and L equal to 2K. And sometimes with the range of the spent by the grayscale referred to the informally as the dynamic image. This is term used and the different way is the different field, and here we defined as the dynamic range of a imaging system to be the ratio of the maximum measurement intensity and minimum detectable intensity level in the system. As a rule, the upper limit is the determined by the saturation and the lower limit is the noise. So we have to see that the upper limit determined is the determined by the saturation and the lower limit by the noise portion. Okay, and the number of the B and bits and required to the store a digitized image, the B equal to M into N into K, and we have to equation become B equal to N root over 2K when and the image can be intensity level. It is common practice to refer to the image and K bit image. We have to see that, for example, an image 256 possible L8 image, the discrete intensity value is the called 8-bit image. Note down the storage requirement. 8-bit image of the size is the higher are the not insignificant, and 124 into 124 and 2KB and equal to B equal to K and B equal to N root over 2K. Okay, then we have to move forward the principle of the linear system. This is the principle of the linear system. What is the linear system? Our system and the entity which act on an input signal and transform it into and the output signal is called the system, and the entity which acts on the input signal and transform it is the output signal called the system. Linear system, a linear system is defined as a system for which the principle of the superposition and the principle of the homogeneity are the valid. So we have to clarify that the linear system. What is the linear system? A linear system defined as a system for which principle and superposition and the principle of the homogeneity are valid. When principle of the homogeneity are valid and the principle of the superposition, this is called the linear system. Okay, this is called the linear system. The superposition principle, the principle of the superposition state that the response of the system to a weighted sum of the input signal is equal to the corresponding weightage sum of the output of the system to each of the input signal. Therefore, if and the input signal x1 and produce and the output signal y1 and the another input signal x2 and produce as and the output y2, then the system is the said to be linear if where a and b are the constant. So we have to see that the superposition principle, this is the one formula is here, the t ax1t and bx1t equal to a1t and byt. So we have to see that the xt is the produced by the output signal, yt y1t is the another input signal, or x says x square t produce and the output, and x2 is then that is the system is the said linear. Okay, then we have to move forward the types of linear system. This is the linear system can be following the two types: linear time invariant LTI system, a system which is both linear and the time invariant is called the linear in time variant system. In other words, a system for which both the superposition principle and the homogeneity principle are the valid and the input output characteristic of the system do not change with time is called linear time invariant system. So LIT full form linear time invariant system. Then therefore the linear time invariant system, the output for the delay input t minus t0 must be equal to the delay output of the yt minus t0. Okay, then we have to see that there is the t yt and t0 equal to y t minus t0. This is the LTI system. It's mean that if the input of the system is the delay unit, then the corresponding output will be also delay. When you have to input the system is the delay, then you have to see that the output will be also delay units. Also for the linear time variant system, all the coefficient and the differential equation and the describing the system are the constant. Okay, then linear time variant, we have to see that the LTV. Then linear time variant is the a system which is the linear time, but the variant is the called linear time variant system. In other words, a system for the which principle of the superposition and the homogeneity are the valid, but the input output and characteristic change with time is called is the linear time variant. This is the LTV system. Okay, therefore for a linear time variant LTV system, the output of the system corresponding to the delay input signal is not equal to the delay output signal. When it's mean the if input LTV system delay and unit, then the corresponding output will be not delay by the exactly times unit. Okay, so linear time variant system is not to linear time invariant system is not same. Okay, also for the linear time variant system is the least one and coefficient and differential equation and describing the system vary with the time. Okay, then we have to move forward the Fourier transform. This is the very important for your GATE exam 2024. So the what is Fourier transform? Fourier transform is a important image processing tool which is used to decompose an image into its the scenes and the cosines components. The output of the transformation represent the image in the Fourier and the frequency domain. Well, the input image is the spatial domain and equivalent the Fourier domain's image each point and the represent a particular frequency and contain the spatial domain image. So Fourier transform is the important image processing tool which is used decompose an image. So Fourier transform used by decompose and the image into the sense of the cosines component. Two types component is used here, one of the sines component and another one is the cosines components. The output transformation represent the image Fourier and frequency domain. The output of transformation represent by two type. This is the one type is the Fourier and another type of the frequency domain. Well, the input image the spatial domain and the equivalent in the Fourier domain image. Okay, the input image spatial domain equivalent in the Fourier domain image, and each point represent a particular frequency and the content in the spatial domain image. So the Fourier transform simply state that that the non-periodic signal whose area under the curves in the finite can also be represented into the integrals of the sines, the cosines after begins of the multiply and the Gaussian of the weightage. And since we are dealing with image and in fact digital image, so for digital image we will be working on the discrete Fourier transform. So we have to see that there is the dealing with the image, in fact digital image, and so for digital image we will be working on the discrete Fourier transform. Okay, and Fourier transform simply state that the one periodic signal whose area under the curve in the finite and can also be represented into the integrals of the sines and the cosines after begin the multiply of the Gaussian weight. Okay, then last one is the consider the above Fourier term and the sinusoid. It is the include three things. First one the spatial frequency, second one is the magnitude, and third one is the phase. The spatial frequency directly relate with the brightness of the image, the magnitude of the sinusoid and directly related with the contrast, and the contrast with the reference between the maximum and minimum pixel intensity, and phase contains the color information. Then we have to see that the Jean the Baptiste Fourier 1768 mentioned that any periodic function can E express as a weighted sum of the sines and the cosines and Fourier series. The function at the bottom is the sum of the four function above. It can express as a weighted sum of the sines and or the cosines. So we have to see that there is the Jean Baptiste Fourier 1768 mentioned that any periodic function can be expressed as a weighted sum and cosine and the sines Fourier series. Then we have to move forward the function at the bottom in the sum of the four function of the above. Then we have to function at the bottom portion, and we have to sum of the function in the above portion. Then it can be expressed as a weighted sum of the sines and cosine. Then we have to Fourier transformation. This was expressed by as a weighted sum and sines and as a cosines or cosines. Okay, then later we for the DIP digital image processing, later for digital image processing it has been adopted, and so we can say it the combined sum of all these wavelength and waves. Then we have to say that the combined sum of the all these wavelength and this wave for the Fourier transformation. Then each line on the digital image can be expressed in the range and sines wave, which is shown in the figure of the different amplitude and frequency. So the Fourier transformation image we can show that this is the two figure and different two figure is here. One is the amplitude and second one is the frequency. Okay, then the cumulative effect of the different frequency and amplitude is the same as the real spatial frequency and distribution of the image after the summation. Okay, there is the cumulative effect of the difference of the frequency. Okay, then is the frequency can be after the summation of the mathematically the technique.
Hello. Hello.
The cumulative effect of the different
Hello. Hello.
frequency and amplitude is the same as the cumulative effect of the different frequency and amplitude is the same as the real spatial frequency distribution of the image after the summation. And mathematically the technique for the separating an image into the various and frequency component is the basically the Fourier analysis. Mathematically the technique for separating and the image into the various frequency and component is basically the Fourier analysis. And the cumulative effect or the different frequency and amplitude is the same as the real spatial frequency distribution of the image after the summation. Okay, in this approach, an image is the separate into its various spatial frequency components and through the application of the mathematically operation and known as the Fourier transformation. Conceptually, this operation and amounts to the fitting a continuous function through the discrete digital number values if they were plotted along each row and column in the image. The peak and valley along any given row or column can be described mathematically by the combination of sine and cosine waves and with the various amplitude, frequency and phase. After an image is separated into this component and spatial frequency, it is possible to display this value in the two-dimensional scatter plot and known as a Fourier spectrum. And Fourier transform of an image, and this purpose of a Fourier transform is to represent a single as a linear combination and sinusoidal signal and the various frequency. So there is the very few characteristic here the Fourier transform. In this approaches the image separated into the various spatial frequency, we can see that the Fourier spectrum the separated into the various spatial frequencies and components through the application of the mathematically an operation known as the Fourier transform. Then we have to conceptually this operation amount to the fitting a continuous function and through the discrete digital number value if they were plotted along each row and
Hello.
column
Hello.
in the
Hello.
image. Then we have to see
Hello.
that the peak of valley along any given row or the column and can be described mathematically by a combination of the sine and cosine waves with the various amplitude and frequency and the phase. And the we have to see the after the image separated into the component spatial frequency, it is possible to display this value in the two-dimensional, okay, and scatter plot and known is the Fourier transform. And Fourier transform of a image, the purpose of the Fourier transform is the represent a single as a linear combination and sinusoidal signal and various frequency. The one-dimensional Fourier transform, we have to see that there is the Fourier transformation continuous case and inverse Fourier transform. Okay, the two-dimensional Fourier transform and it inverse Fourier transform continuous case, and this is the inverse Fourier transformation. The formula of the Fourier transform in the continuous case. Okay, then we have to see that this is the discrete Fourier transformation, actually the simple Fourier transform, so it contains some sample that the denoted an image, and in the above formula f x and y denote the image and f u and v denote the discrete Fourier transformation. The formula for two-dimensional inverse discrete Fourier transformation to given below. Okay, the inverse and the discrete Fourier transformation the convert the Fourier transform back to the image. Okay, this is the Fourier transformation formula is here, and we have to see that there is a several type and several object and features is Fourier transformation is here. Okay, this is the figure 7.22. This is the figure of the 7.22 the satellite image. This is the image that is the image the Fourier digital image in the A, and this image is the digital image, and this is the Fourier transform spectrum image. Fourier transform spectrum image. The lower frequency in the scene are plotted at the center of the spectrum, and the progressively higher frequency are the plotted the outward. So we have to see that there is the lower we have to see that the center of the spectrum progressively higher frequency are the plotted of the outward. Okay, then the common and application of the Fourier analysis. So there is the elimination of the image noise, and figure 7.24 is the airborne and the multispectral scanner image the containing subsystemnal noise. The Fourier spectrum for the image is the shown is the figure 7.24. Note that the noise pattern which is the awkward in the horizontal direction in the original scene and appears as a band of frequency and trending in the vertical direction in the Fourier spectrum. In figure 7.24, the vertical wedge and block filters has been applied to the spectrum. This filter pass the lower frequency components of the image but block the high frequency component of the original image and trending in the horizontal direction. Show the inverse transformation. This image, the A is the A image. This is the A, this is the B, this is the C, and this is the D image. C is the show that the inverse transform. This is the inverse transform. This is the inverse transform, and the vertically wedge and block filter has been the applied to the spectrum. This filter passed to the lower frequency and component of the image, but blocks are the high frequency component of the original image and trending in the horizontal direction. Okay, thank you. This is our short and very few information about the Fourier transform and sampling and quantization. Okay, thank you everyone.